Assalamu alaikum wa rahmatullah. This is solid modeling course using Inventor. This is lecture number 10. Today we'll talk about how to use Inventor in order to say make a gear design, and then we will talk about dynamic simulation, just demonstration, and stress analysis. In general, gear design or dynamic simulation or stress analysis, it needs actually all of them needs a good background, theoretical background, subject background about how to design gear, how to do dynamic simulation, what's the dynamic simulation, what's the dynamic system, how we can do it, and also regarding the stress analysis, what's the stress, what's the strain, what type of stress, what type of strain, how we can calculate it. All of these information should not be given in our course or in this lecture. This lecture just how to use Inventor. Inshallah, you will take course design 1 and design 2 course for mechanical engineers, and in that course you will learn the alphabet or the rules or how we can design gears, shaft, brakes, everything, and you will gain the experience and get the theoretical background for gear design, dynamic simulation, stress analysis. And maybe your instructor in that course will ask you to do some projects using Inventor, Autodesk Inventor. So my task today, or my say target today, to tell you or give you just introduction about gear design, dynamic simulation, stress analysis using Inventor. I will not go deeply in that topic, just give you a demonstration. Let me start by gear design. For the gear design, guys, surely because we have a gear, not we have a part, maybe one gear or two or three, and we have we can say that a built-in parts in Inventor, like built-in functions in MATLAB or programming language. We have a built-in parts like gears, shafts, and these things. We can just say that call this parts from the Inventor. How we can do that? Regarding the gear design, it should be in the assembly, not part. So what I will do, guys, I will close this part, go to new file. It depends on units you have. You have English or metric. Say that I have metric. In the metric, see, we have part design, we have assembly. I will choose the assembly. Go to the assembly drawing, select standard assembly IAMM, then create, then say OK. Now, before starting the Inventor, let us talk about some gear terminology. Again, these informations should not be given in this course, but to learn how we can use it in Inventor, let us just talk about them. Let us know what they are. Guys, gear terminology, as you see, if you have two gears mated together like this, we have something called, if you see this dashed circle, this one called the pitch diameter. Pitch diameter, it's an imaginary circle where the two gears mating together or touch together each other. We have also here F, the face width, here called circular thickness. This one, the smaller diameter, it's called root diameter, from root to root. Also here, the difference between the pitch diameter and the say that the root, it is the dedendum. The other one, it is addendum. We have working depth, we have circular pitch, outside diameter. So these well-known terms, when you go to a design course and take how you can design the gear, you have to define all of these. Now, in this PowerPoint, guys, I want you just to read what's the pitch diameter, what's diametral pitch, what is the module. As example, the module used in metric units, it is the pitch diameter divided by the number of teeth, the metric equivalent of diameter pitch. Diametral pitch in metric, it's in metric units, diametral pitch. In inches units, called module. So it depends. Number of teeth, it is N. Diametral pitch, it's P. Pitch diameter is D. What they are. Actually, I will not go through them. I will not teach you what they are. You will take them in the design course. But this is what we have here. Center distance is very important to understand. The center distance, it is the distance between the center of the first gear and the second gear. And it's diametral pitch of the first one plus the second one. Circular pitch also. We have many terminologies: addendum, dedendum, hole depth, working depth, circular thickness. This is not included in the exam. They will not be included in the exam, guys. Okay, face width, outside diameter, root diameter, pressure angle. I wrote this sentence just to show you what they are. And again, not included in the exam. I should not give you these informations in the Inventor course, solid modeling course. Just to know that if you want to design a gear, use Inventor, you have to go to the background, theoretical background, and get your data from there as a designer. So we are now just using these informations, what we had before, and we want to model the design. So how we can, I told you, open for gears, open the assembly. From the assembly, we have to go to design. As you see, design here. In design, we have bolted connection, we have clip spin, you have frames, you have here shaft, gears, bearing, belts, keys, springs. We have many things. We will take just one example, the gears. If you go to here for gears, you have spore gear, you have worm gear, we have bevel gear. I will use the spore gear, the well-known one. Spore gear. We need design accelerator. You must save the assembly document before creating. Okay, I will save it. Keep it in the current folder. My current folder, it's download, where I have all of the parts. Name it assembly 1. It's okay, save it before that. Okay, waiting for the Inventor now. As you see, these are the spore gear component generator. Okay, now as you see here, to design a gear, all of these, see, we have design guide, desired gear ratio, module, center distance, gear number 1, its component, number of teeth, face width. All of these data, guys, should not be taken from solid modeling course. It should be taken from the design course. So you have to design your gears there, and then come here to implement your design using Inventor to do some analysis and so on. So here, as example, this tool will generate 2 gears, mated gears. The gear number 1 and gear number 2. So as you see here, gear number 1, it is component. There is a component which is gear number 1. Gear number 2, there is a component which is gear number 2. Now, what is the design criteria? Here, it depends on, it could be module and number of teeth, center distance, and so on. I will use the center distance. So what is the desired gear ratio? Keep it like this, 2.47 as example. What's the module? It is 2 millimeter. What's the center distance? Say it is 80, and so on. Number of teeth for the first gear, 23, face width, everything. Now, guys, the second one like this, just calculate to be sure that everything okay. The Inventor will calculate everything, the other things. If you selected the center distance, just put the center distance module, and the tool will calculate everything. After calculating, guys, we got everything. Say okay. As I show you, say okay again. Just waiting the Inventor. I see we got this assembly. As you see, we have gear number 1 and gear number 2. Okay. Now by default they are grounded. We can remove the grounded. Now let me start the exercise. Again, I will go to File, New File, say that metric units assembly, create, OK. I will go then to Design. From the Design, I will go to the gears, spore gears, save it as assembly number 3. It is OK. It's OK. As you see, I will keep the same criteria. It is center distance. The center distance, it's 80 millimeter. Module, it is 2 millimeter, and desired gear ratio, and then calculate. The tool will calculate everything else. Now, guys, regarding gear number 1, as you see here, we have gear number 1 and gear number 2. Gear number 1, 23. Gear number 2, it's larger, 57 teeth. Okay, so I will keep just the smaller gear, and I will delete the large gear. So I will go to gear number 2 here. See, its feature, no model. Say no model. Now this tool will create just one gear, the smaller gear. As you see, this is the gear. This is the smaller gear. As you see here in the assembly browser here, it's gear number 1. Here we have the origin of the gear number 1, X, YZ plane, XZ plane, XY plane, X axis, Y axis, Z axis, center point, and so on. Keep them like this. Now, guys, what I'm trying to do, I will try to do mating gears, 2 mating spore gears. Okay, and three. 2 large gears, and at the middle we have small gear. The small gear, it is a drive gear, while the other driven gears. So what I will do, I will see this one grounded. At the beginning, I will right click on the gear number 1, remove grounded. Remove ground, because this is a gear, it should rotate. If it's grounded, it will not rotate. The degrees of freedom will be 0. Now, degrees of freedom, they are 6. It can move in X, Y, Z direction, and it can rotate around X, Y, Z direction. What exactly I want this gear to do, it will be at the center of the file. And it should just rotate around the Z axis only. So I have to prevent movement in X and Y. I have to prevent rotation around X, around Y. And I should keep the rotation around Z axis. The rotation around Z axis. Okay? Now, how can I do that? At the beginning, let me say that we have the origin of the file and we have the gear origin. Let me say that I want to go to assembly. If you remember, from the assembly, I have to say that make a constraint, choose a constraint. As example, I want to mate. As example, let me show you what I will do. I was thinking to do the following. I will try to make, as you can do, we have different methods, but let me mate this back surface of the gear with the X, the file XZ plane, no XY plane. So I'm mating the back face of the gear with the XY plane. Apply, cancel. As you see here, let me go to here, show you. It can move, but let me show you from the front view. From the front view, it can move freely. But go to, as example, top view. See, in top view, I can't move it in XY direction, in Z direction, just in X direction. Okay, and still it rotates around its axis. Okay, next step. How can I fix the center or the axis of the gear in the axis of the file? Okay, let me go back to the home like this. I want to make this gear Z-axis in the Z-axis of the file. So I will go to Constrain. I will go to Z-axis of the gear. See, I'm choosing this one, Z-axis of the gear, with Z-axis of the file. So I will make them without offset. Apply. We have a problem here. The assembly, let me choose, say that the second option here. I will do it again. I will say mate the gear Z-axis first with the Z-axis of the file and choose this one aligned, apply, cancel. Now see, the gear can't move in Z-axis, Y-axis, Z, everything, but it can rotate around its Z-axis, and this is what I want to do. Let me go to front. This is what I want to do. See, I can't move it up, down, left, right, but still it rotates around its axis. Now I will go back to design. From design, I will choose a gear, keep the same settings as you see, okay, same calculations, but I will go to gear number 1 component. I don't want it. So I will make no model for gear number 1, and for gear number 2, I will choose a component. So as you see, here we are producing the larger gear. Calculate, okay. We need the first one like this, and we need the other one like this. I will do it later. Okay, now as you see, we have two gears here. Two gears should be mated together. Okay, this gear, as you see, has 6 degrees of freedom. The first thing, guys, we want to constrain this gear. I will go back to assembly. I will go to constrain. From the constraint, as example, we can make a flush. I want the surface, top surface of this gear to be parallel to this gear. Apply without offset. How can I see the effect? See, now because this surface parallel to this surface, I can move it in Y direction, but I can't move it in Z direction. Okay, so it's free in Z direction. Now, how can I control the distance between the center of the first gear and the center of the second gear? Okay, so that the teeth of the larger gear touch the teeth of the smaller gear. If you remember, let me go back to design. Let me go to small gears. Use the same calculations. The center distance, it is 80. So the distance between the Z axis of this gear and this gear should be 80. So we'll go to assembly, go to constrain. From the constraint, we want to constrain the axis of this one. How can I choose it? See, we have the file origin, we have gear number 1 origin and gear number 2 origin. So go to gear number 2 origin, the z-axis, I will mate the z-axis of the larger gear with the z-axis of the smaller, or the file, better, the file, because they are same. Okay, with offset how much? It should be 80. Okay, apply, not working, I will choose the other option again. So again, z-axis mate, z-axis of the large gear with the axis of the file, and use aligned with 80 distance, apply, cancel. Now you see the gear just rotate around its axis and around the other gear. Okay, now how can I fix it in a correct position? Let me go to the larger gear, say that, let me talk about the z-axis. This z-axis, I will make it visible. I can't see it, never mind. I will go to the file, XY plane, no, say that this plane, XZ plane, I will make it visible just to show you. When this gear in its correct position, the z-axis of the larger gear mate with this plane. So what I will do, I will make a constraint mate the axis, the z-axis of the larger gear with this YZ plane, the file YZ plane, apply, cancel without offset. Now let me go back to that YZ plane, make it invisible. Now see, the gear, it should rotate around its axis and at the same time joined with the smaller gear, and everything else not allowed. See, I can't move it up, down, I can't move it left, right, but it should still rotate around its axis. I will do the same thing, for the second gear, the third gear. But before that, we have to make a relation. If I remember, the smaller gear, it's a drive gear. The right one, it is driven gear. So how can I relate them? What type of constraint we can add? It is a motion constraint. Motion constraint. I see we have two types: rotation, translation. Here we have rotation. I will choose rotation. We have here, see, forward or reverse. Let us start forward. So see, when this rotates, this will rotate with it. Apply the ratio, it is 1. By the way, this is design value, should be given from the design. It depends on number of teeth and diameter. So as you see, they are opposite. It should be when this rotates counterclockwise, this should rotate clockwise, but I see the opposite. So I will go back to this relation. It's mate, sorry, not this one, rotation, right click, edit, and choose the reverse, apply, cancel. See now, now they are, okay, but the ratio should be fixed in a good way. Or let me delete. We can go again to constraints, which is better. Constraint, say motion constraint, rotation. I will select the inner area. Say that as example. Say that this area with this area, it's okay also with this area, apply, cancel. Let me go to front again. All of these should be a design, but the opposite also. Let me go back, edit. It is in forward. I will choose the reverse. Now see, they are, but the value should be the value, this one value, it is 0.4. What meant by 0.4? It meant that one revolution from the first one, if the first one rotate, say that one revolution, the second one will rotate around 0.46 rotation. So this one should be fixed from design. You have to calculate number of teeth and diameter, and also the rotation speed. There are some calculations should be done in design course. Anyway, say that it's okay. Now for the next gear, the left gear, we will go again back to design, again to sport gear. From the sport gear again, we need the second larger gear. So keep gear number 1, no model, keep gear number 2, component, keep same calculations, and say okay, this is the second gear, larger gear. Same story guys, same story. We can go to design, assembly, constraint. We'll start by flush, make this surface and this surface, they are parallel without offset. Okay, then we have to constrain the axis distance between the z-axis of this one and this one, or the origin of the file. Constrain, same story exactly. Constrain, I will constrain for the fourth gear. I will open or expand the fourth gear, the third gear, sorry. Go to origin. I will choose the z-axis to be mated with the file z-axis, with offset 80, as I told you before, because the center distance between the center of the large gear and small gear should be 80, and we know that it should be aligned. Apply, cancel. If you see from the front view, they are mated together, but still the larger gear rotate around the smaller gear. How we can fix that? By fixing the location of the z-axis. Now, let me show you the z-axis of this gear. Let me, we are talking about gear number 3. We need the z-axis to be mated, so constrain the mate the z-axis with what? With x, y, or x, z, or whatever. I will show you. I will go to the origin, mate it with this gear, this work plane, make it visible. I will constrain the z-axis of this gear, as you see, mated with this work plane without any offset. Apply. See, now still it rotates around its axis, so I will hide this work plane. I will go to bottom or to the top view, rotate like this. This is the gear, still this is the gear, okay? This one, the previous one, this is the gear. We want to just add a more constraint, motion constraint, like the other one. Motion constraint, rotation, it's in reverse. This is the first rotation, this is the second rotation, and here we have to keep a good ratio in between. Apply, cancel, as you see. Now, how can I demonstrate the motion? How can I record a movie? If you remember, I told you about the drive. How can I drive this motion? Actually, regarding assembly, done. But if you want to demonstrate the motion using drive, we have to add a constraint. As example, let me go to the gear, smaller gear, because the smaller gear is the drive gear. Let me go to the origin of this gear. Let me take or select the YZ plane. Let me make it visible. As you see, we can see it. Okay, anyway, if you when gear rotates like this, the YZ plane rotates with it. So let me say that I want to add a more constraint, extra constraint, just to drive. I want it as an angle, as example, direct angle. I want this work plane to be mated with the origin YZ plane, okay? Now currently it is 0, never mind, apply, cancel. Now it will not rotate, see? Why? Because I added an extra constraint just to drive. Now I will go to this angle, drive this angle, and say that run from 0 to 10 degrees, go back, run from 0 to 100 degrees, as example, run. See, this is faster because the relation should be fixed here and here. We can also record, remember, we can also record the demonstration. So, as I told you, this angle not needed for the assembly, but needed to make drive. Thank you so much for the first part of this lecture. Hi, again, this is the second part of this lecture. We will talk about the dynamic simulation demonstration. We finished the gear part. Now we will go to open. I have an assembly already. I have this assembly. I did this assembly before. Say this is the assembly, this mechanism assembly. And as you see, in this assembly, we have this link. It's fixed, grounded, and this one can rotate, as you see. And I want just to make dynamic simulation demonstration, how we can use the dynamic simulation in Inventor. It's just a quick introduction about it. If you want in details, you have to get the dynamic simulation theoretical background. So we have, as you see, we are in the assembly now. We will go to environment. From environment, we have different tools. One of them stress analysis, frame analysis, and we have dynamic simulation. I will start the dynamic simulation. As you see, this is the dynamic simulation. If we run the simulation, by the way, I have previous settings here, but I will teach you how to use it. Say that I will close it again, finish dynamic simulation. I will go back again to environment, dynamic simulation. At the beginning, I have to choose this one to start from the construction mode. By the way, it could give you a message to start tutorial. You can skip it. and then go directly to construction mode. In construction mode, you can change the settings. This is from the previous. I will go to, it should be by default like this. Okay, and this torque should be deleted because added before. Now, as you see, this is the current situation. If you run dynamic simulation, we don't have anything to do because I don't have settings. So we can go back to the construction mode. As you see, in the construction mode, we have a gravity. If you have a force, just gravity, we can right click on the gravity, define the gravity, okay, remove the suppress, then select intensity, say that the gravity should be parallel to this line, as you see, and it is to the opposite direction, and the value of gravity, we know the value how much. We should not change it. Okay, baby, as you see, once I started dynamic simulation, the assembly will be converted, as you see, to standard joints. You can remove joints, you can edit joints, you can add more joints. Say that I will go to joint number one. Joint number one, as you see, we have this mate and this mate, and this one, revolution number one. I will right click on it, say properties, just to show you we have some dynamic properties here. In general, you can see if there is, let's say that force or torque on that joint, or number of degrees of freedom. Here we have initial conditions. We can change the initial conditions, position, and something like that. And here we have also we have some joint properties like torque. We have friction here, as example. The drive friction coefficient is 1. Make it 0.5 as example, just to show you that there are some settings also here. Edit imposed motion. We have some settings, we have to prepare it. Second thing I want to tell you guys, before that, let me again, I added just what? A gravity. For gravity, see, this is the dynamic simulation for, let me make it for 200 seconds. Now this is just dynamic simulation with effect of gravity. We don't have drag force from air, we don't have other forces, just gravity and some friction in the joint number one, and not modified to the other joints, just joint number one. Stop it. Okay. Second thing, guys, say that I want to show in a graph. Let me expand it. Show in a graph the force, the displacement and the velocity of the first joint only. Let me go back to edit mode. Okay. Just to remind you, I'm focusing on joint number one. I added on properties something here in the torque, which is friction, 0.5 coefficient. Okay, so what I will do, guys, I will go to here, the output grapher here, output grapher. This output grapher, just wait because it is consume a little bit time, just seconds. Okay, this is grapher. Let me take the assembly to the left and expand this one. As you see here is the tool, simulation player. Here the assembly, and this one the grapher. You can expand the grapher down and to the right like this. And as you see in the grapher, we have revolution number 1, number 2, number 3, number 4, 4 joints. See, for the first joint in this grapher, we can see the position of the first joint and velocity. For second one, position. For third one, position. So what I will do, guys, I will skip this one. Click and wait until this disappear. Next, I will remove the position of the second joint. Same, click. This will disappear. And keep just the position and velocity for the first joint. And maybe we can change the time. Maximum it should be 200 seconds. I will take just 5 seconds only. Okay, and let me show you what will happen here. Run the simulation. As you see, while the assembly demonstrate the motion or dynamic simulation like this. See, this is the red one. It is the velocity of revolution number 1, joint number 1, and this one in pink, it is the displacement. You can take this data to Excel sheet. You can print them. You can do what you want. We are simulating just for 5 seconds. Done. It's very easy steps, but to do real dynamic simulation, you have to go deep in how to use dynamic simulations. The Inventor, it is just a tool, but there is some theoretical background. You should gain this experience. As example here, just we have some simulation settings here. You can change them. You can export to finite element. You can do many things. Now let me change the gravity, and let me add another say that torque. There is a torque, drive torque. I will go back to construction mode, and from the construction mode here, see, we have force, we have torque. Say that I want to add a torque. How much this torque? Say that 200 Newton meter. This torque location, say that on this joint. Okay, the direction of this torque, as you see, it is inward. I think I can't see it. Okay, it is inward, so that still you have to indicate a direction. We can see that the torque direction in this one, like this. Okay, apply. Okay, let me see the effect of this torque on the simulation. Again, for 5 seconds, again, run the simulation. See now the graph, the values are different than before. Stopped. So you can add forces, you can add torques, and then do the simulation. You can export this data to Excel sheet, and you can do some analysis on it. This is how we can use the dynamic simulation. Again, if you want to change anything, it should be in the construction mode like this. Okay. Next topic, guys, finish dynamic simulation. Next topic, it is the stress analysis, how we can do the stress analysis. In stress analysis, guys, say that I have this part, and I know that this part from here, it should be fixed or mated with other, as you see here, mated with other link. So it should be fixed here. And there is also another link mate with this, with the part from left. But this one, it is fixed, and this one, it's movable or subjected to a force or bearing force, maybe torque, maybe anything. So let me start. First of all, I will go to open the file I have. I have this file. This is the part file. Before starting simulation, let me check. Okay, now again, we will go to environment. Again, we are in the part file. Okay, go to environment. From environment, select stress analysis. Before starting the analysis, guys, before making simulation, let me check the loads. I don't have some load here. I don't have constraints. Okay. The first step, guys, we have to add constraint. This constraint, it is fixed. Now, as I told you, if you remember, as I told you, this here, it should be fixed from here. So I will try to select this one and this one, and this surface also, this surface and this surface. Oh, by mistake, I selected the upper one, cancel. Let me go back again, check, there is no constraint here. Fixed, I will select the inner surfaces. Okay. This one and this one, done. Apply. As you see, once I selected the fixed, go to constraints here. See, we can see the fixed constraint. Can I edit or delete? Yes, right click, edit or delete. Next step, we want to add the load. Add the load. For the load, we have load, force, pressure, bearing force. The situation in our example, it's bearing force. How much the bearing force? It is 100 Newton. Where is it in this surface? Direction opposite or like this, say that like this, okay? Apply. So I have the load here and I have the constraint here, which is fixed. Now I can make the simulation. Let me go to the home, okay? Why simulation is simulation? Because I want, as a designer, I want to know what or where the maximum stresses that can happen due to this situation of fixed constraint here and bearing load here. Where is the maximum stress should be, and then is it critical or not? So or the displacement sometimes. Simulation, as you see, run your simulation and wait for the inventor. See, the inventor give us, as you see to the left here, results. it shows us the von Mises stresses. Von Mises stresses, again, we are here not to talk about these stresses. You will take them in the design course or strength of material course. So here, how we can do the simulation, regardless what they are. As you see, the red color show you the maximum stress. It is 95.59. So it's critical here. And where is the location? At this area. At this area. Now we can do something. We can put a probe to show you the stress here, how much. As you see, von Mises stress here. We can right click finish and we can move it to here. We can add another probe just to show a comparison to here. Right click, we can move it to here. Now we can also do animation of the stress and record it, by the way. You can record it. Now see, it is just 10 steps, fast steps. Let me stop. Let me make it slower by selecting 20 steps and run the simulation. As you see, here will be the maximum stress. Stop. Do you want the first principal stresses as example? Double click here. First principal stresses. We have to stop before that. Okay. Wait for the inventor. Double click here. Now this is the first principal stress. Same thing. Third principal stress. If you want displacement, double click on displacement. See, this part will move in in Z direction more than others. Now again, you can make a probe also, probe here to show you the displacement. Right click finish. You can move it out like this. Okay, and again animate to show the displacement. See the maximum displacement here or deflection here from the left side. Now say that, by the way guys, do you want to see, because the stress analysis done by something called finite element analysis, and the tool to be used in finite element, it's the mesh. You can see the mesh here, mesh view. You can change some settings, mesh settings from here if you want to do certain finite element analysis and so on guys. And also you can, by the way, you can make a report. Don't make it complete. You can custom as you select it from here. You can change some properties, then press OK, yes, and wait for the inventor to produce the report. As you see the report, it will be like a web page or split in a web page. See, analysis, this is crankshaft part name. As you see here, density. By the way, I forgot to do something regarding dynamic simulation and regarding stress analysis. You have to assign material for the part before that. But I will go back to this point later. As you see, density, by the way, the material added into Inventor, it's stainless steel 440C. Density for this one known. Mass of this part, this is the mass. The area of this part, the volume. See here we have as example the average element size, minimum grading factor, and so on. Here we have general mass density, yield strength, by the way, yield strength, ultimate tensile strength, Young modulus, Poisson's ratio, shear modulus, and so on. And you can also have I think center of gravity. As you see, this is center of gravity, and so on. And this is the dynamic simulation, the stress analysis we did before. See, this is the report generated for my simulation. I selected all of these before. So here you can print it as a PDF and share it with others to check your design. Can I change the load? Yes, surely. You can go to load as example here. The load, it's bearing load. I will delete it. Say that I will delete the mesh also. Okay, keep this one. I want not the displacement. I want the result to be von Mises stresses. Okay, and let me go to, as you see, we have fixed constraint here, and we don't have loads. I will go to load, add as example, I will add a force. Where is this force? As example, this force on this surface. How much the force? Say that 200. Direction of the force to up or down, say up. Apply, cancel. I will make simulation now, run the simulation. and then animate. See, when you say that 20 steps, run. When you push this part by a force with 200 Newton up in Z positive direction, we expect the stresses to be from back to here, maximum stresses, because this analysis shows us this one. Regarding displacement, as I told you before, we can go to here. Just wait for Inventor. Double click on displacement. You need X displacement or Y displacement or Z displacement. Surely we are thinking about Z displacement. Say that I want a torque, not a force. Let me go to load, again delete this force, right click, delete, and then go to moment. See this moment? I will add moment on this surface as example. What's the value of moment? Say that 500 Newton meter. Direction, say that direction, it is this direction, like this. Okay, I think I did a mistake. Cancel. Go back again to moment. The moment on this surface, direction is good here. Just give the value 200 as example. If you want to change direction, say that direction, it is I don't have a line, I want a line, just line like this, and choose the opposite direction like this. Apply, cancel. Now this is the torque on this face. Do the simulation and see the result. Run the program. So expect it to deflect to the left. Okay, let me, this is displacement. I will show the, no, stress, sorry. So I will make animation, 20 steps as example. You can record them if you wish. Run the analysis. I'll see when you apply the torque, it will be like this. We expect here to be the location of the maximum stress. So it depends on the part application you have. I think this is more than enough to talk about stress analysis. It's just a tool, use finite element using Inventor. We can implement or say that do some stress analysis. But to do that, we have to get some background about finite element and how we can use stress analysis. I think it's enough for this one. By the way, just the material. See here, the material here, the material, it is stainless steel. How can I change the material, guys? We have to finish, or let me right click here, assign material. You can go to material from here and select the other material. That's it. Or before do the analysis, finish the analysis, before do the analysis, you can go to crankshaft IPT, right click, I properties. From I properties, go to physical. From the physical, as you see here, we have a stainless steel. You can change it to aluminum or what, titanium as example, apply, and so on. So I think this is more than enough. It's just demonstration, introduction about how to use gears, how to use dynamic simulation and stress analysis. Thank you so much. See you in next video.